The focus of this year's Nobel Prize in Physics is quantum mechanical entanglement. Alain Aspect, John Clauser, and Anton Zeilinger, this year's Nobel laureates in physics, have taught us how particles that are in entangled states can be investigated and controlled. Already in the early years of quantum mechanics, entanglement stood out as a key property of the theory, with non-intuitive consequences, possibly indicating that hidden variables were missing in the quantum mechanical description. Later on, in the 1960s, John Stuart Bell made a theoretical discovery that hidden variables theories, assuming locality, cannot explain the quantum mechanical predictions. This year's laureates have, through groundbreaking experiments with entangled photons, established the violation of Bell inequalities. In addition, their methods have paved the way for quantum information science and a new era in quantum technology, where intense research is underway to build quantum computers, improve measurements, and establish secure quantum encrypted communication. Our first speaker is Alain Aspect. He was born in Agen, Lot-et-Garonne, France in 1947. He studied undergraduate physics at École Normale Supérieure de Cachan and also at Université d'Orsay, from which he received a PhD in 1983. He is currently Augustin Fresnel Professor at Institut d'Optique at Université Paris-Saclay and Professor at École Polytechnique Palaiseau. So please join me in welcoming Alain Aspect to the stage to tell us about the development that led to this year's prize.
Dear colleagues, ladies and gentlemen, so this lecture will be about entanglement, how entanglement nowadays becomes a tool, and how images as strange as non-locality can help having, it's not a little too strong? No, it's okay. How the concept of non-locality can help having intuitions about these applications of entanglement. So the story of entanglement has a milestone in 1935 when Einstein and Bohr started discussing, and Schrödinger added his grain of salt, and the conclusion was that entanglement is really amazing. But it took another almost 30 years for John Stuart Bell to discover that not only it's amazing, but it's different from any previous mysterious behavior of quantum mechanics, and this was with the famous Bell's inequality. I think it's a little too strong. Okay. And then another 20 years almost, and Feynman recognized that entanglement being different, probably we can do something with it, and he published this famous paper, which is considered the founding paper for, let's say, quantum computing. And so there is a problem. Hein? C'est la faute aux lunettes. Ah bon, d'accord. là là. Merci. And this is maybe part of a new quantum revolution. So let us start. I will explain what is the Einstein-Podolsky-Rosen situation. I will present it with photons, Bell theorem, and then the experiments that have been done with photon, of course focusing on our experiments, and a comment about, in my opinion, the interest of thinking with images of non-locality. So let us start. You all have heard that Einstein had a problem with quantum mechanics. Well, I should start my clock because otherwise I will speak too long. You know, people who know me know that. Okay. Einstein had a problem with quantum mechanics that he was worried that quantum mechanics makes probabilistic prediction. He fully agreed on the result of the calculation, but he thought that a theory that makes probabilistic prediction cannot be an ultimate theory. It must be a kind of statistical theory, but there should be below description of individual objects. Like for instance, in this room, if I think of the velocity of the molecule which are here, I can describe by a probability, what is the probability that the velocity is between 300 meters, 310, etc. But we have no doubt that each molecule has its own velocity. That's probably what he had in mind. And he made all efforts to find situations in which, by logical reasoning, he came to the conclusion that you need to introduce this underlying level. There is a famous Solvay conference of 1927 where he tried, and each time Bohr replied successfully saying, no, 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 you cannot describe more precisely. But this was about a single particle. In 1935, he came with a new situation involving two particles, two entangled particles, and then, once again, he came to the conclusion that you need to complete the theory. And in spite of the denegation of Niels Bohr, one could say that the situation was unsettled. So what is the Einstein-Podolsky-Rosen situation with photons, as the experiment that we have done? You have a photon going to the left, a photon going to the right, and we are going to make a polarization measurement. So this is a polarizer. If a beam of light polarized along the direction of the axis of the polarizer, light will go along +1 channel. If it is polarized perpendicular to A, it will go into the -1 channel. And if it is polarized at an angle with A fraction will go up and a fraction will go down. But if now I have a single photon, a single photon cannot be split. You cannot have a fraction of the photon up and a fraction down. And so comes the probability. If you have a single photon, you have a certain probability to go up and a certain probability to go down. And these are single probabilities. And there is another kind of probability which is extremely important, is a joint probability. Probability for a given pair, what is the probability to get +1 here and +1 here? This is called the joint probability for polarizer in the angle A, in the direction AB. Now comes entanglement. What Einstein, Podolsky, and Rosen found is that this state is permitted by the formalism, by the mathematics of quantum physics. Why is it interesting? A state XX would describe two photons polarized like that. A state YY would describe two photons polarized like that. But the superposition of XX and YY, I cannot tell you it's like that or like that. The point is that these states cannot be factorized, and because it cannot be factorized, you cannot attribute a given property to the first one and a given property to the second one. This is entanglement. When you have a state like that, it's an elementary exercise in quantum physics to calculate the various probabilities, single probabilities and joint probabilities. And I will focus on the case where the two polarizers are parallel to each other, so the angle AB is 0. Single probabilities are 1/2, and joint probability are 1/2 for P++ and P-. And this means perfect correlation. Maybe you are not fully convinced because 1/2 does not look as a perfect correlation, but look. Here the probability to get +1 is 1/2, and the probability to get +1 and +1 is also 1/2, which means that the conditional probability to get +1 on the second side, once you have obtained +1 on the first side, this conditional probability is perfect, is 100%. Okay. Now comes the question that naive physicists like me ask all the time. Okay, I have the result of a calculation. I would like to understand, and in my mind, understanding means making an image which makes sense. And the problem is that the standard way to doing this calculation does not allow me to make an image which makes sense. And the reason is that when you have two entangled particles, the calculation is done in an abstract space, a mathematical space, called the Hilbert space tensor product of the space for each particle. Whatever, it's an abstract space. And it's very difficult to make an image in our space starting from that space, except that there is a, and so it's annoying. Excuse me. Sorry for people that I wake up, okay? It's annoying not to be able to make images because, as a famous quantum optics theorist said, quantum phenomena do not happen in a Hilbert space. They happen in a real laboratory, and a laboratory is our space. So I insist, I want an image in our space. And there is a way to do that. It's a standard quantum calculation, a little more complicated. We will separate the two measurements. We will first make a measurement here, and then a second measurement here. And the first measurement here can give either result +1 or -1, and we assume the polarizer along X, and so result +1 corresponds to polarization X, result -1 corresponds to polarization Y. Now, what I do is that I must use the so-called projection postulate, which tells me that just after the measurement, then I must project the initial state onto the eigenstate associated to the result. Let's do it for the first case. For the first case, the result is XX. Now it's no longer an entangled state. It's a state where the two photons are like that. So I know that the second photon is like that. If the result was Y, then the projection would give YY, and now I know that the two photons are like that, and the second photon is like that. Okay. So we know that immediately after this measurement, the second photon falls, so to speak, in a state which is the same as you found here. And then, of course, it's trivial to find that you will get the full correlation, because if you find +1 here, you find +1 here, etc., etc. So we fully recover the prediction of quantum mechanics, but in addition, now even we have an image in our space, reduction here, etc. But there is a catch. The measurement on the first photon seems to influence instantaneously at a distance the state of nu2. And of course, this was unacceptable for Einstein. And this is why Einstein said we must add something to quantum physics. So let's go to try to add something, and this was Bell's theorem. The idea is the following. When I have two measurements at a distance which are strongly correlated on two objects which were emitted from the first place, It's very natural to say, okay, when they were emitted, they have a joint property, and it is this joint property that determines the result. For instance, we could have polarized photon from the beginning XX, and then we are going to have +1, +1. We could have YY, and we are going to have -1, -1. So the idea is to introduce this supplementary parameter, completing quantum mechanics, finding an underlying structure. And this is an idea, if you think of it, which is very natural. Our colleagues in biology have no doubt that if you measure color of eyes or some diseases on twin brothers, the reason why you find a perfect correlation is that they have the same chromosome. So the idea is that there may be some kind of chromosome for the two photons to understand this correlation. Bohr disagreed. Why did he disagree? Because he had the deep feeling, intuition, call it as you want, that if he would accept to complete quantum mechanics, it would no longer be self-consistent. But it seems to me, when you read Bohr, that it was a deep conviction. It was certainly not a demonstration as clear-cut as the one of the Solvay conference of 1927. And so you could stay with the idea that it was a discussion between Einstein and Bohr. But 30 years later, well, 29 years later, Bell came and said, okay, let us take seriously the proposition that to understand the correlation, we must introduce supplementary parameter. And so we are going to introduce a function whose value is +1 or -1, depending on lambda and on the orientation of the polarizer. Similarly here, and of course, the various pairs don't have the same lambda, so we need to introduce a density of probability, which is well behaved. And now if we want to calculate the so-called correlation coefficient, it's nothing else than the average of the product AB over these various lambda. This is John Bell in front of a nice scheme of experiment with, whoops, sorry. And Bell's theorem says that no local hidden variable theory, that is to say, no theory completed in the idea that you have a common property, which is local, I will come to this point, can reproduce all quantum mechanical predictions for the Einstein-Podolsky-Rosen correlations. This is how it works. Bell can demonstrate that if we express the correlation coefficient with the capital A and capital B, and we consider two orientations on the first side, A and A prime, two orientations on the second side, B and B prime, and we look at the four possibilities, AB, AB prime, etc. Then, this quantity S that you calculate with capital A, capital B, and rho cannot be bigger than 2 or less than -2. But let us look at the quantum mechanical prediction for this coefficient. This is calculated by the 1/2 of cosine squared, etc. Quantum mechanics predicts that for a perfect EPR state, this correlation coefficient takes this value. And now consider this special set of orientation with an angle pi/8 here, here, here. If you put that and calculate it, it's not a difficult exercise. You will find that S is equal to 2√2, which is obviously bigger than 2, which means that no local hidden variable theory can reproduce this quantum mechanical prediction for this set of angles. And now, the possibility to complete quantum mechanics is no longer a matter of taste. Up to this point, you could think that, okay, Einstein and Bohr disagree on how to interpret it, but both agree on the result of the calculation. So if you are pragmatic, you are in your lab, you do experiment, you explain it with quantum mechanics, as my friend Bill Phillips say, shut up and calculate and observe what you have. Okay. I cannot resist showing that the demonstration of Bell's inequality is so simple that everybody should understand that it is simple. The idea is very simple. You want to calculate the average of this quantity, and you are going to consider the four possibilities with A prime, and B prime. And the quantity that will give the quantity S that we hope is obtained as an average of this formula. And honestly, to demonstrate that this can only be +2 or -2 is an exercise of a high school pupil, okay? Because here, look, it's just that, and it will be either +2 or -2. And then you take the average. And it's not rocket science to understand that the average of a number, which is either +2 or -2, has to be between +2 and -2. So you see, Bell's inequality is really something extremely simple. Cannot be wrong. I speak several times of locality, and Bell's locality condition is the following. To demonstrate its inequality, you need explicitly to assume that capital A cannot depend on B, capital B cannot depend on A, and this, which means that the result of the measurement here cannot depend on the orientation of the other polarizer, and vice versa. And moreover, the way in which pairs are emitted here cannot depend on the orientation of the polarizer that will make the measurement. This makes sense, of course. However, how do we know that there is no interaction between the various parts of the experiment? And so, in his founding paper, Bell insisted that if you could do an experiment with polarizers whose orientation are modified during the flight of the photon, you change the orientation, and then there is no possibility, according to Einstein's relativity, that there is an influence from here to there, and even less an influence of the orientation onto the way it was emitted before. So this was in the conclusion of Bell's paper. And really, it seems to me, this is why I was so interested by this conclusion. It seems to me that in an experiment with variable polarizer, we address a full conflict between quantum mechanics and Einstein's worldview, which is physical reality and locality based on relativity. Okay, so it is time to go to experiments. And of course, here I will be fast because my colleagues are also going to describe experiment. There were two sets of experiments. The pioneers, and John Clauser is here, and Ed Fry is here also. It was between 72 and 76. Then there is a series of Institute Optique experiments in 81 and 82. I started in 75, but the experiments were in 81 and 82. And Jean Dalibard and Philippe Grangier, who participated in the experiment, are here also. And then there was other set of experiments, and including the experiment of Anton Zeilinger and colleagues, and he will explain us. So these are the pioneers. I will go fast because I'm sure that John will go in detail. But the idea is that this experiment found that quantum mechanics is upheld and that Bell's inequality are violated. However, these experiments were still quite far from the ideal scheme that I presented at the beginning. It was fantastic, but it was not yet the scheme. And this is the reason why I embarked into this program with the goal to develop experiments as close as possible as the ideal scheme of the theorist. And to make a long story short, this was the core of the experiment. Many lasers and atomic beam, etc. But at the end, it was possible to excite calcium atoms to this level. John Clauser and Stuart Friedman has also done that. But in that time, they did not have the lasers that I had. And so they excited here, and sometimes they have the right pair of photons, and other times they did not have it. With this two-photon excitation, it was fantastic because it was a very pure source and moreover, very intense. We could get 100 of coincidence of real signal per second. Maybe you are not impressed. 100 per second? Well, think. 100 seconds gives you 10 to the 4. And now the statistical accuracy with 10 to the 4 is 1%. So in less than 2 minutes, we got a 1% accuracy. John, it took him hours to have, or maybe days to have this accuracy. So this was a good starting point, and of course we repeated his experiment, and we confirmed that the experiment of John and of Ed Fry indeed were working, because our first scheme was like their experiment. Then comes the first original experiment. In all previous experiments, the polarizers were polarizers where you get the +1 result, but the -1 result is lost. And this obliges to make auxiliary calibrations, which complicated the situation. Here, I could afford to have beam splitters, which are polarization beam splitters. So in other words, it's a polarizer like the ideal one I presented on my ideal scheme, where the result +1 is detected here, and the result -1 is detected here. And now it's fantastic, because in a single run with orientation A and B, you have the 4 counting rates. And once you have the 4 counting rates, you are all you need. The correlation coefficient is nothing else than this numerator plus for similar result minus for diagonal result, okay? And it's self-calibrated. You plug into the denominator the sum of the 4 numbers, and that's it. No auxiliary calibration. And this experiment was done by Philippe Rangier in his master thesis. And the result is here. It's absolutely fantastic. The green curve is a prediction of quantum mechanics, taking into account the slight inefficiency of the experiment. Polarizers are not perfect. You have solid angles. It's detailed. We know how to calculate it. Philippe can tell you that we calculated that before, and then we did the measurement, and it came exactly on that curve. And the violation of Bell's inequality was by more than 40 standard deviation. You know, in CERN, when they have something at 3 standard deviation, they leak the information that there may be something. And at 5 standard deviation, they are happy and they publish. Here it was 40 standard deviation, so no discussion. But now, you understand that my initial goal was to make an experiment in which we change the orientation of the polarizers. And this is the kind of polarizer we have. We have them in the windows of Institut Optique. And it's a piece of equipment like that with LED screens, etc., like 50 kilograms, okay? We are not going to rotate 50 kilograms in 10 nanoseconds. So the idea was the following. If we could build a switch which either let light go to a first polarizer in orientation A or to a second polarizer in orientation A prime, if the switch is fast enough, it's equivalent to a single polarizer switch from A to A prime back to A, etc. Same on the second side, and that's it. In the experiment we had, the time between 2 switching was 10 nanoseconds, and 10 nanoseconds is definitely less than the time it takes for light or for the photon to go from the source to here, which was 20 nanoseconds in our experiment and 40 nanoseconds between both ends. This is one of the switches that we built. Actually, there is a first version of these switches which has been given to the Nobel Museum. So if you go to the Nobel Museum, maybe you can see it. The experiment was a little more difficult. It was a little longer. We had to accumulate for tenths of minutes rather than minutes, but okay, it worked. And at the end, we found a violation of Bell's inequality by 6 standard deviations. And for the first time, Bell's inequality had been tested with polarizer set at the last moment. I will just say a few words of the third generation of experiment because I am sure that Anton will elaborate on that. There was again a big progress on the source of entanglement. My source was better than the previous one, but their source was much better. The idea was to use a nonlinear phenomenon called parametric down conversion. The important thing is the following. Because of some technical feature which is called phase matching, the two photons are emitted, the two entangled photons are emitted in extremely well-defined direction. And you can inject them into optical fiber. And once it is injected in optical fiber, then you can stretch the fiber for hundreds of meters. And this is what Anton and Greg Weiss did in Innsbruck. He will explain that. And here I just want to say that the same year, Nicolas Gisin was able to inject his photon in the commercial network of Swiss Telecom and to observe entanglement at 30 kilometers, which is amazing. Okay, there have been a lot of discussion about loophole-free experiments, etc. I have no time to comment about that, but eventually, in 2015, there were 3 experiments published closing the loopholes, and Anton was one of them. And if you want to know more about it, you can look for this paper, which is easy to find on the web. It's a News and Views competitor of the one of Nature. It's a News and Views of the American Physical Society. So here you have my comments about these experiments. So Einstein's local realism is untenable. Violating Bell's inequality means that you cannot stick to the point of view of Einstein. What can we conclude? Well, Einstein himself told us. Einstein did not believe in what he said. Yes, he was reasoning ad absurdum. He told us, if I was not right, this is what you would have to accept. But now we know that we have to accept it. And what we have to accept, these are the words of Einstein. Basically, it's the fact that when you do something on the first system, it instantly reacts on the other one. This is called non-locality, quantum non-locality. And for concluding, I'm just going to show you one example of why I think that non-locality is fruitful as an image. It's about quantum cryptography. Cryptography is the fact that 2 friends, Alain and Bob, want to communicate, and you have a spy, an eavesdropper, who wants to intercept the message. And they want to be sure that nobody can read their message, can understand their message. And for that, there is a method which has been demonstrated by Shannon as absolutely sure, that a method called one-time pad, in which Alice and Bob have 2 identical series of random 0 and 1. Alice uses this series to code, Bob uses same series for decode, and you can demonstrate, it's a mathematical demonstration, that it is absolutely sure. It's absolutely sure provided that the message, sorry for that, too fast, provided that the message is not longer than the key, because otherwise there are irregularity and the people, who, the eavesdropper are very smart and they are going to find a solution out of it. So the point is how to distribute 2 identical keys to Alice and Bob, who are far apart, without the eavesdropper being able to make a copy of the key, because if he makes a copy, then it will be easy to decipher the message. Entangled photons are a solution. This is a method of Arthur Eckert. You remember what I told you? If Alice and Bob have the same direction for their polarizer, either you get +1 and then you get +1, or you get -1 and you get -1, and each is absolutely random. So you have 2 identical series of random numbers. Now, what about the spy? Why is it safe? It's safe for the following reason. If you believe what I told you, non-locality, it's at the very last moment that you get +1 or -1, and immediately you get the same thing on the other side. There is nothing to spy in between. The decision, the result is not yet here, okay? And so there is nothing to spy on the flying photon, but because it's only at the last moment that you will have the result. So here, non-locality tells us it should be safe. Of course, there is a big demonstration when it is finished, mathematics and everything, but in my opinion, all the idea is here, and this is why I like non-locality. This kind of experiment has been demonstrated at more than 1,000 kilometers by Jianwei Pan from the satellite launched by the Chinese. So, conclusion, non-local images provide fruitful intuitions. And to conclude, I have several thanks. First, of course, these people, because it is these people who pointed out the extraordinary character of entanglement, which is now at work in developing quantum technologies. I want to thank two master students who participated in the experiments. I already named Philippe Brangier, but there is also Jean Dalibard. You don't recognize them, so if you want to talk to them, because both are here, now they rather look like that, okay? I, of course, want to thank two engineers, one in mechanics and optics, one in electronics, who were very helpful to develop the experiment. I had a lot of equipment built in the workshop of Institut d'Optique and also from the workshop of Centre Études Nucléaires de Saclay. It was not perfectly legal, but now it's more than 30 years ago, so I can say it. I want to mention Christian Imbert, who was professor at Institut d'Optique. He was the one who handed me the paper of John Bell, saying, look into that, there may be something interesting for you. And that was a starting point. And then at that time, when I decided to embark into that, there were many criticisms that it was useless research, etc. And he always protected me. Unfortunately, he passed away, but I owe him a lot. I owe a lot to the book of Claude Cohen-Tanuji, Bernard Dieu, and Frank Galloway, because it is a book in which I learned quantum mechanics, which allowed me, when I read the paper of John Bell, to totally understand the quantum reasoning in the paper of John Bell. And Claude Cohen-Tanuji also educated me a lot by his lecture at Collège de France. It's very well known in the medium, and for me it's crucial. You know, I never learned quantum mechanics or quantum optics at school or at university. I learned it by this way. And last and not least, I want to thank my family, and especially Annie, who supported me, my children who accepted maybe my too long hours in the lab, okay? And I think that they are very important for this success. Thank you very much.